August 17th, 1943, 3:47 a.m. RAF Thurleigh, Bedfordshire, England. The control tower operator checked his watch for the third time in as many minutes, then looked out across the darkened airfield. Beyond the runway threshold, barely visible in the pre-dawn darkness, sat 53 B-17 flying fortresses. Their engines were silent, their crews were not yet aboard. But in exactly 13 minutes, the first bomber would begin its takeoff roll, and in the 78 minutes that followed, all 53 aircraft would be airborne, formed up, and heading toward Germany. This was no ordinary mission. This was the first deep penetration raid to Schweinfurt and Regensburg, a mission that would require precise timing, split-second coordination, and a takeoff procedure so dangerous that it would claim aircraft before a single German fighter was even encountered. The procedure was called Minimum Interval Takeoff, or MITO, and it would become one of the most hazardous yet essential operations in the entire strategic bombing campaign. The problem that changed everything. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. In the early months of daylight bombing operations over Europe, assembling a bomber formation felt like a careful piece of choreography. Deliberate, procedural, safe, each group of heavy bombers, lifted from its grass or concrete strip at scheduled intervals, climbed in gentle arcs, and joined the formation in what aircrews liked to imagine was an organized, almost civilized ritual. Pilots and navigators trusted the rules 2 or 3 minutes between takeoffs, circling the field while climbing, flares and hand signals from the ground to mark assembly points. For a handful of formations operating in clear skies, the system was adequate. It was sensible. It kept men alive on the ground and in the air. But the campaign's scale changed the rules the way weather changes a planned route. What had worked for raids of 50 or 100 aircraft did not survive contact with an industrialized air war. By mid-1943, the 8th Air Force was producing 600 and 700 aircraft missions. By 1944, raids that would have been unthinkable a year earlier, hundreds and sometimes thousands of heavy bombers launched from dozens of bases were no longer theoretical but routine. The sky above England, once a stage for incremental sorties, became a torrent of metal and flame, all trying to get airborne, climb, and assemble before the day slipped away. Major Curtis LeMay, then commanding the 305th Bomb Group, saw the problem with a clarity that made other commanders uneasy. LeMay was a navigator by training and an engineer at heart. He thought in numbers, in fuel curves and climb rates, in spacing diagrams on paper. He did not romanticize the formation, he calculated it. When he ran the arithmetic on the existing assembly practice, the results were stark. If the 8th Air Force persisted with 2 to 3 minute takeoff intervals and leisurely circling climbs, a 1,000-bomber mission would be unworkable, not in a matter of hours, but in a matter of practical catastrophe. 6 hours of takeoffs and assemblies translated into fuel wasted, while planes sat circling and waiting, increased exposure to changing and worsening weather, and an unrivaled opportunity for German radar and fighters to observe, target, and scatter seams in the plan. Worse still, engines running at full power for long periods increased the risk of mechanical failure. More aircraft in the same airspace meant a higher chance of mid-air collisions. The calculation was clinical. The existing doctrine was a bottleneck that would strangle the strategic bombing campaign at the moment when the Allied demand for massed bombing power became absolute. LeMay's answer was blunt and uncompromising. Compress everything. If the mission demanded thousands of aircraft in the air in a single window, then the takeoff and assembly process had to be shortened to its practical minimum. 2 or 3 minutes between liftoffs became 30 seconds. The hour of circling were to be replaced with immediate, assigned altitudes and headings. Stragglers would be an accepted loss at the assembly point. Schedule and timing had to matter more than perfection. In LeMay's view, the calculus of risk shifted. The near-term danger of mechanical or pilot error during compressed takeoffs was preferable to the strategic danger of a campaign that could not mass its forces and strike decisively. Put in blunt terms, LeMay proposed to break the rules. Aviation handbooks, teeth, and all warned against such close spacing on the takeoff roll and against multiple heavy bombers climbing through the same airspace on converging courses. The new plan meant aircraft of 60,000+ pounds fully loaded would be rolling into the sky with barely a runway's length between them, climbing on collision courses and trusting rigidly timed vertical and lateral separations to keep them from becoming a mid-air disaster. For crews taught to value caution, the proposal read like a dare. The human reaction was predictable. Curiosity edged with dread. For ground crews, it meant readjusting the choreography of runways, tow trucks, and engine checks. For pilots and co-pilots, it meant rehearsing throttle runs and shortening decision loops. Bombardiers and navigators studied new profiles, straight climbs to assigned altitudes, instead of circling climbs that gave them time to breathe and check instruments. For commanders, the proposal was an ethical tangle: press men into a novel, more dangerous procedure, or risk strategic impotence and possibly higher loss rates because the formations could be intercepted piecemeal. LeMay did not theorize from an armchair. He tested. The 305th Bomb Group became the lab for the experiment. Early trials were, by many accounts, both promising and terrifying. When runs went right, the benefits were immediate and undeniable. Aircraft were airborne and stacked in assigned altitudes in a fraction of the time. Fuel consumption on the ground was reduced, and the window of exposure to enemy observation and fighter interception narrowed. When runs went wrong, the consequences were stark, and sudden engines overheat under sudden loading. Pilots misjudge climb profiles. Wake turbulence makes close climbs precarious, and a single error could put 2 or 3 aircraft on a trajectory to collide. Much of LeMay's genius lay in mitigating the risks without surrendering the speed. He treated the procedure as an engineering problem and attacked it with the tools of training and standardization. Takeoff clearance procedures were rewritten as unambiguous checklists: exactly when to advance throttles, when to rotate, when to adjust flaps, and when to begin the climb. Each aircraft was assigned a precise heading and altitude to achieve within a narrow time window, sometimes within seconds, so that the columns and stacks of bombers would separate cleanly in the vertical plane rather than depending on imprecise lateral spacing that could collapse in gusty conditions. Training shifted accordingly. Pilots practiced minimum interval takeoffs on grass strips with dummy sequences before trying it with live engines and full loads. Ground controllers learned to use light and radio signals to keep the sequence tight. Maintenance teams focused on ensuring engines were at peak readiness. A compressed takeoff process could survive only if the mechanical baseline was reliable. The command culture under the pressure of war changed. Commanders authorized risk as a necessary cost of achieving mass. Beyond the procedural changes, the psychological effect was profound. Crews, who had previously reported for missions with a mixture of resignation and routine, now faced a sharpened edge of anxiety. The compressed process placed a premium on concentration and split-second decision-making. Men had to trust each other more than ever: the pilot on the runway ahead, the ground crew who waved the green light, command voices who would not delay for human hesitation. The compressed procedure also forced crews to confront a different sense of mission tempo. There was no longer a long luxury of circling and rechecking, only a tight, synchronized surge into the sky. Operationally, the payoff validated the risk calculus. Compressed takeoffs and instant altitude assignments allowed the 8th Air Force to move from an attritional, drawn-out departure pattern to a concentrated, almost industrial sortie rhythm. Mass could be assembled in hours rather than half a day. That meant more bombs on target in shorter windows, less fuel wasted in climbing and waiting, and a diminished opportunity for German fighters and radar stations to interfere before the formations were airborne and en route. Crucially, the standardization and practice reduced, not eliminated, the sting of accidents. Near misses became teaching moments, procedures were refined, and an institutional memory of what not to do developed fast. There was a cost, and it should not be minimized. The compressed procedure increased the risk of accidents during takeoff and the early climb. Some crews never quite grew comfortable with the intimacy of close sequencing. Errors did happen. Engines failed under sudden load. Wake turbulence from heavy aircraft could buffet following ships in unexpected ways. In the worst cases, those near misses resulted in loss. LeMay and others faced criticism, sometimes muted, sometimes sharp, about exposing crews to heightened danger to solve a logistical problem. The ethical tension balancing acceptable risk to one's own men against the strategic need to bring decisive pressure to bear on the enemy became one of the defining moral decisions of the air campaign. Yet, context mattered. Luftwaffe, opposition, radar warnings, and the unforgiving North Atlantic weather ensured that the alternative slower assembly often meant even greater danger, in the form of failed missions, lost surprise, and wasted resources. The compressed assembly was not a reckless gambit but a hard calculus. Accept measurable risk on the ground for a higher probability of mission success over enemy territory. In time, what began as a risky experiment hardened into doctrine. Other groups adopted the minimum interval takeoff and strict climb profiles, improving the 8th Air Force's ability to mass its strength and execute precision routing to targets deep in Germany. The campaign's logistics maintenance cycles, crew rest, fuel planning, evolved to fit the new operational tempo. And LeMay's reputation, already notable for being demanding, became synonymous with the aggressive problem-solving mindset the strategic air war required. If the compressed takeoff procedure changed the way bomber wings left their bases, its larger significance was conceptual. It transformed how air power planners thought about mass and risk. War does not reward aesthetic safety. It rewards solutions that accept certain local dangers to achieve strategic effect. The problem LeMay solved was not merely an operational bottleneck. It was a lesson that in large-scale war, the interface between human limits and mechanical performance must be engineered precisely and sometimes ruthlessly to meet the scale of the task. The sky above England never quite returned to the image of comfortable circling formations. It became, for a time, a tightly ordered instrument of industrial warfare, columns rolling in quick succession, altitudes assigned and achieved with the precision of a factory assembly line. The new system did not remove fear or danger, it reframed them. Men who had once trusted routine now placed their faith in timing, in checklists, and in the ruthless arithmetic of strategy. What began as a problem, how to assemble thousands of heavy bombers in a single effective striking force, ended as a transformation, an acceptance that to operate on the scale modern war demanded required new rules, faster tempos, and a willingness to trade a degree of individual safety for collective capability. In the calculus of the 8th Air Force, that trade would leave behind bitter memories, but also a changed air campaign, one capable of bringing unprecedented pressure to bear on an enemy that had thought the British sky theirs to watch. A minimum interval takeoff for heavy bombers was, in the words of one pilot, the closest thing to a controlled crash sequence you could imagine while still calling it safe. The procedure began hours before the first engine started. Ground crews would position aircraft nose to tail along the taxiway leading to the runway, spacing them approximately 50 yards apart. Bombers would be loaded, fueled, and armed in position. Crews would board their aircraft while still parked, conducting pre-flight checks from their assigned spots in line. At the designated start time, precisely synchronized across all participating airfields, the first aircraft would begin its takeoff roll. The moment its tail wheel lifted off the ground, signaling rotation, the second aircraft would begin rolling, not when the first aircraft was airborne, not when it had cleared the runway. The instant rotation occurred, the next bomber started moving. 30 seconds. That was the interval. 30 seconds between a 65,000-pound bomber beginning its takeoff and the next one starting its roll on the same runway. For perspective, a B-17 required approximately 3,500 feet of runway to reach takeoff speed and become airborne under full combat load. At rotation, traveling roughly 100 miles per hour, the aircraft would use another 500 to 800 feet before actually leaving the ground. This meant that when the second bomber began its takeoff roll, the first bomber was still ON, The runway, struggling to gain altitude, engines straining under maximum power. If anything went wrong, if an engine failed, if the aircraft couldn't gain sufficient speed, if wind shear pushed it off course, the bomber behind it would have less than 20 seconds to react. At full takeoff weight, a B-17 needed over 1,000 feet to stop from takeoff speed. There would be no stopping, there would be no aborting, there would be only collision. Lieutenant Robert Morgan, pilot of the Memphis Belle, described his first MITO experience. You'd be sitting on the taxiway, watching the bomber ahead of you start rolling, and you're thinking, that guy better not screw this up because I'm about to follow him down that runway, whether he's still on it or not. Your co-pilot is watching the clock, counting down seconds. 15. 10. 5. At 0, you're rolling, no matter what. You can see the bomber ahead, maybe 500 feet in front of you, engines roaring, struggling to get airborne. And behind you, another bomber is about to start chasing you down the runway. It was terrifying every single time. Once airborne, the compression continued. Standard climb-out procedures called for aircraft to gain 1,000 feet of altitude before making any turns, providing separation from terrain and other aircraft. MITO procedures eliminated this safety margin. Aircraft were assigned specific headings and climb rates immediately after liftoff. Lead aircraft might climb straight ahead at 500 feet per minute. The aircraft behind them would offset 30 degrees right and climb at 450 feet per minute. The third aircraft would offset 30 degrees left and climb at 400 feet per minute. Telling and preparing this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. The result was a carefully choreographed ballet of 50-ton aircraft, all operating in the same airspace, separated by hundreds of feet instead of thousands, climbing through clouds and morning darkness with dozens of other bombers from other groups doing the exact same thing from nearby airfields. Weather made everything worse. England's infamous cloud cover meant that bombers often entered clouds seconds after takeoff, flying on instruments through a sky filled with other aircraft, unable to see anything beyond their own wingtips, trusting that everyone else was exactly where they were supposed to be, climbing at exactly the rate they were supposed to climb, all while fighting turbulence that could toss a bomber hundreds of feet off course in seconds. Captain Harry Crosby, the lead navigator for the 100th Bomb Group, documented one particular MITO in his diary. Entered clouds at 800 feet, didn't break out until 15,000 feet. Flew on instruments for 23 minutes through soup so thick you couldn't see the wing from the cockpit. Knew there were at least 40 other bombers in those same clouds. Every few seconds, you'd see a shadow flash past, or catch a glimpse of a wingtip, or hear engines that sounded too close. Made it to assembly altitude with the whole group intact. Found out later that the 95th Group, forming up in the same airspace, lost 2 aircraft to collision. They never even got a radio call-out. Just vanished into the clouds. Breaking through the clouds into clear air above brought only temporary relief. The next phase, assembling hundreds of individual bombers into organized combat formations, presented its own deadly challenges under MITO procedures. Pre-war bomber doctrine called for aircraft to assemble into groups of 18 to 21 bombers, arranged in a 3-dimensional combat box formation designed to maximize defensive firepower. Each bomber occupied a specific position in the formation lead, high right, low left, tail end Charlie with precise distances and angles maintained between aircraft. Under standard procedures, groups would form up individually, then join together into wings, and finally combine multiple wings into divisions. The process was gradual, allowing time for adjustment and correction. Under MITO procedures, everything happened simultaneously. Multiple groups would be climbing through the same airspace, all trying to form their combat boxes, all following precise but dangerously close timing sequences. Assembly ships brightly painted obsolete bombers, flying distinctive patterns would lead each group to their assigned assembly points. But with dozens of groups assembling simultaneously, the sky above England became a 3-dimensional chess game, played at 200 miles per hour, with pieces that weighed 30 tons each. The margin for error was measured in seconds and feet. A pilot drifting 100 feet off course during assembly might slip into another group's airspace. An aircraft climbing too fast might emerge directly beneath another bomber. A navigator miscalculating wind correction by 5 degrees might aim his entire formation into another group's assembly area. Major Robert Rosenthal, who would survive some of the war's most devastating missions with the 100th Bomb Group, described the organized chaos. Imagine trying to arrange 350 aircraft into precise formations, while all of them are moving at 180 miles per hour, climbing through 20,000 feet of airspace, in a volume of sky perhaps 50 miles across and 5 miles deep. Now imagine doing this in less than an hour. Now imagine that if you screw it up, people die, missions fail, and the entire bombing campaign grinds to a halt. That was assembly under Mito. Every single time felt like threading a needle while riding a roller coaster. The complexity multiplied with the number of aircraft involved. A 100-bomber mission might involve 5 or 6 groups, each assembling independently in designated areas before combining into a single stream. A 500-bomber mission required coordinating 25 groups across multiple wings and divisions. A 1,000-bomber mission, which became increasingly common, in 1944 meant 50 or more groups all assembling simultaneously across the entire southeast of England. Visual reference points became critical. The bomber's distinctive assembly ship's aircraft painted in wild geometric patterns, polka dots, stripes, or checkerboards served as gathering points for each group. Pilots fresh from takeoff would scan the sky for their group's assembly ship, join up on it, and gradually form the combat box. Meanwhile, other groups would be forming around their own assembly ships, all visible in the same airspace, all potential sources of confusion if a pilot locked onto the wrong reference point. Radio discipline became essential. With hundreds of aircraft on the same frequencies, unnecessary chatter could drown out critical instructions. Controllers issued terse commands: Baker Group, Angels 22, Vector 090. Translation: climb to 22,000 feet, turn to heading 090 degrees. Pilots acknowledged with single clicks of their transmit button. Anything more than absolutely necessary information was forbidden. Yet even with perfect execution, assembly under Mito procedures was never completely safe. The statistics tell the story. Between 1,943 and 1,945, the 8th Air Force lost 248 bombers to operational accidents during takeoff and assembly aircraft that never encountered enemy action, destroyed by mid-air collisions, mechanical failures during high-stress operations, or disorientation in clouds leading to controlled flight into terrain. That's 248 bombers, approximately 2,480 men, lost before ever reaching enemy territory, the equivalent of 12 entire bomb groups. More losses than the Luftwaffe inflicted on many individual missions. And yet, Mito procedures remained essential, because the alternative slower, safer assembly would have made the entire strategic bombing campaign impossible. The true brilliance of minimum interval takeoff procedures emerged when examining the raw numbers involved in strategic bombing operations at scale. Consider Operation Argument, better known as Big Week, conducted in February 1944. Over 6 days, the 8th Air Force launched 3,300 heavy bomber sorties against German aircraft manufacturing facilities, 3,300 individual bomber missions, each aircraft requiring takeoff, assembly, bomb run, and return. Using standard takeoff and assembly procedures with 2-minute intervals and 90-minute assembly times, those 3,300 sorties would have required roughly 183 hours of continuous operations just for takeoff and assembly, impossible to accomplish in 6 days, even with perfect weather and no aircraft malfunctions. Mito procedures, by contrast, allowed complete groups of 50 to 70 bombers to launch and form up in 90 minutes. A single airfield could launch all its assigned bombers for a mission in under 2 hours. Multiple airfields operating simultaneously could put 1,000 bombers in the air, formed and heading toward Germany, in less than 3 hours from the first takeoff. This compression enabled operational tempos that would have been impossible otherwise. Missions could be launched based on weather windows that might close within hours. Multiple waves could be sent against the same targets, arriving at different times to maximize damage and confuse defenses. The 8th Air Force could respond rapidly to tactical opportunities, striking targets while German forces were vulnerable. The fuel mathematics were equally compelling. AB-17 burned approximately 200 gallons of fuel per hour at cruise power. Reducing assembly time from 2 hours to 90 minutes saved 100 gallons per aircraft. For a 100-bomber mission, that translated to 10,000 gallons of fuel-saved fuel that could be carried as additional bomb load or used to extend range. For 1,000-bomber missions, the savings reached 100,000 gallons, at $4 per gallon in $1,944, that represented $400,000 saved per mission, or roughly $7 million in modern currency. Over the course of the campaign, MITO procedures saved an estimated 50 million gallons of aviation fuel, the equivalent of 2,000 railway tank cars. But the real advantage wasn't just operational or economic, it was strategic. MITO procedures enabled the 8th Air Force to achieve the concentration of force necessary to overwhelm German defenses. 100 bombers arriving over a target within a 10-minute window, properly escorted by fighters, could saturate German interceptor capacity. The Luftwaffe might scramble 150 to 200 fighters to defend a critical target, but those fighters could only engage a limited number of bombers effectively before running low on fuel and ammunition. If the bombers arrived in a compressed, coordinated stream rather than dribbling in over an hour, German fighters had fewer opportunities to land, rearm, and attack again. General Curtis LeMay, by 1944 commanding the entire 3rd Bomb Division, explained the strategic calculus. Every minute we could compress assembly and departure was a minute the Germans had less warning, less time to react, and less opportunity to concentrate their defences. MITO wasn't just about efficiency, it was about shock. We wanted to hit them with overwhelming force before they could fully respond. That required getting hundreds of bombers over the target in the minimum possible time window. The compression also reduced vulnerability to German fighters during the climb to altitude. Under standard procedures, individual bombers or small groups would be climbing toward assembly altitude for extended periods, often without full fighter escort, making them vulnerable to opportunistic attacks by German fighters patrolling the English coast. MITO procedures meant bombers reached combat altitude quickly, already in defensive formations, with fighter escorts positioned to protect the entire stream. Behind every statistic, every efficiency gain, and every operational advantage lay human beings executing procedures that required absolute precision under extraordinary stress. The pilots bore the primary burden. A B-17 pilot during MITO operations had to maintain exact airspeed within 3 miles per hour while positioning his aircraft in 3-dimensional space relative to dozens of other bombers, all while monitoring 4 temperamental radial engines, coordinating with a crew of 9 other men, following radio instructions from ground control, referencing visual cues from assembly ships, and doing all of this while wearing an oxygen mask at altitudes where a single mistake could trigger hypoxia within seconds. First Lieutenant John Lucky Luckadoo, who survived 25 missions with the 100th Bomb Group, described the physical and mental demands. Your brain is processing 50 things simultaneously during MITO. You're flying the aircraft manually, no autopilot during assembly, so you're constantly adjusting throttles, trim, and control pressure. You're listening to multiple radio frequencies. Your co-pilot is calling out airspeeds and altitudes. Your navigator is giving you headings. Your flight engineer is monitoring engine instruments. Your bombardier is confirming bomb load status. And all the while, you're watching the aircraft around you, maintaining position, adjusting for wind, compensating for weight changes as you burn fuel. It's like playing 3-dimensional chess while running a marathon while someone shoots at you. And during MITO, before you even reach Germany, you're already exhausted. Co-pilots served as critical safety backups, cross-checking instruments, monitoring fuel states, and watching for traffic conflicts. During MITO procedures, co-pilots would often lean forward against their restraints, craning their necks to maintain visual contact with nearby aircraft, calling out warnings. Bomber at 3 o'clock high, 200 feet. The physical strain of maintaining this vigilance for hours led to neck injuries, muscle strains, and chronic pain that many co-pilots carried for the rest of their lives. Navigators faced their own unique pressures during MITO operations. They had to calculate precise headings accounting for winds that changed with altitude, plot courses that would bring their aircraft to exact assembly points at exact times, coordinate with other groups to avoid conflicts, and constantly update their calculations as conditions changed. A navigation error of even 2 or 3 degrees during assembly could cause a bomber to miss its formation entirely, leaving it isolated and vulnerable once over enemy territory. Flight engineers monitored the mechanical health of 4 engines, each developing 1,200 horsepower and spinning at 2,700 revolutions per minute. During the high-power operations required for MITO maximum throttle for takeoff, sustained high power during rapid climb engine temperatures would spike toward critical levels. Engineers would watch cylinder head temperature gauges like hawks, ready to alert pilots if conditions approached dangerous thresholds. Engine failures during MITO were frequently catastrophic because the aircraft was at low altitude, heavy with fuel and bombs, and operating at the edge of performance limits with little margin for error. Radio operators managed communication between aircraft, with ground control, and with fighter escorts, all while dealing with German radio interference designed to jam Allied frequencies. During critical phases of MITO operations, radio operators might be switching between 5 or 6 different frequencies, filtering signal from noise, and relaying information to pilots who had mere seconds to react. Gunners during MITO operations served primarily as additional eyes, scanning the sky for collision threats and calling out traffic. But they also prepared for combat by charging weapons, checking ammunition belts, testing turret motors, and donning the bulky heated suits necessary for survival at high altitude. All of this occurred in spaces barely large enough to turn around, with temperatures plunging below zero as altitude increased. The psychological pressure was immense and cumulative. Pilots and crews knew that a single mistake during MITO could kill not just themselves, but potentially dozens or hundreds of others. A mid-air collision during assembly wouldn't just destroy 2 aircraft. The debris, the fire, and the shock could trigger a cascading series of collisions as other aircraft swerved to avoid the wreckage, crossed into other formations' airspace, or lost control in the chaos. These weren't abstract risks. They were real probabilities that every crew member understood intimately because they had all witnessed MITO accidents. They had all seen the flash of a mid-air collision in the clouds. They had all watched bombers drop out of formation with engines smoking, desperately trying to find an emergency landing field before crashing into the English countryside. They had all attended memorial services for crews who never made it past the English coast. The stress manifested in different ways. Some pilots developed pre-mission routines bordering on superstition, always entering the aircraft from the same side, always touching a specific part of the fuselage before boarding, always performing the pre-flight checklist in the exact same order. Some crews flew entire missions in near silence, speaking only when operationally necessary. Others engaged in constant nervous chatter, filling the intercom with jokes and commentary to manage anxiety. Medical officers documented physiological impacts. Average heart rates during MITO procedures ranged from 120 to 140 beats per minute, sustained cardiovascular stress equivalent to moderate intensity exercise. Except the crews were sitting relatively still, the acceleration coming from adrenaline and stress hormones rather than physical exertion. Blood pressure readings showed consistent elevation. Sleep studies revealed that bomber crews averaged 4 to 5 hours of sleep per night during intense operational periods, accumulating sleep debt that compounded mission after mission. The psychological toll extended beyond individual missions. Bomber crews were required to complete 25 missions before rotation later increased to 30, then 35, as the war progressed. Each mission involved at least one MITO departure, and often a challenging return, with battle damage, wounded crew members, or mechanical failures. The cumulative stress of repeatedly executing these precise, dangerous procedures, dozens of times, under combat conditions, broke men. Combat fatigue, what we now recognize as post-traumatic stress disorder, was epidemic among bomber crews by late 1944. Medical records show that approximately 30% of bomber crews suffered from some form of combat-related psychological condition. Many were grounded before completing their tour. Some suffered complete breakdowns, unable to even approach an aircraft. Others powered through their missions but carried the scars for decades afterward. As MITO procedures became standard across the 8th Air Force, continuous refinement addressed the most critical safety and efficiency challenges. Radio technology improvements in 1944 introduced VHF sets with better clarity and range, reducing communication confusion during assembly. New radio protocols designated specific frequencies for specific phases of operations: takeoff frequency, assembly frequency, combat frequency, reducing crosstalk, and improving coordination. Improved navigation aids, including the British BABS, Blind Approach Beacon System, and American APN, 1 radar altimeters, gave pilots better situational awareness during low-visibility operations. These systems allowed more confident MITO operations even in marginal weather, expanding the operational windows available. Assembly procedures evolved with experience. The introduction of GH radar bombing systems in late 1944 allowed bombers to form up under overcast conditions, following electronic signals from ground stations rather than relying purely on visual assembly. This reduced the collision risks during the most dangerous phase of operations. Fighter escort coordination improved dramatically. By mid-1944, P-51 Mustangs were timing their takeoffs to rendezvous with bomber streams at specific points, reducing the time bombers spent without fighter protection. This required even more precise timing during MITO operations, but the payoff in reduced bomber losses was substantial. Training innovations addressed the human factors. Synthetic trainers allowed pilots to practice MITO procedures on the ground, building muscle memory and decision-making skills without the risk of actual operations. Formation flying training increased from a few hours to 40 to 50 hours, with specific emphasis on operating in close proximity to other aircraft during high-stress maneuvers. Crew training emphasized standardization. Every pilot learned the exact same procedures in the exact same order. Every co-pilot used the same call-outs at the same decision points. Every navigator calculated winds using the same methodology. This standardization meant that crews from different groups could fly together if necessary, all operating from the same playbook. The introduction of experienced lead crews, specially trained teams that would fly at the head of formations, improved overall mission effectiveness. These lead crews received extra training in navigation, bombing, and formation leadership. During MITO operations, less experienced crews would simply follow the lead aircraft, reducing individual decision-making burden and improving formation cohesion. Airfield improvements directly supported MITO operations. Runways were extended from 5,000 to 6,000 feet, providing additional safety margin for heavy takeoffs. Taxiways were widened to accommodate larger numbers of bombers marshalling for departure. Hard stands the concrete. Parking areas for individual aircraft were positioned to optimize flow toward the runway, reducing taxi time and improving departure sequencing. Weather forecasting became more sophisticated. The 8th Air Force employed dedicated meteorological units with access to weather reconnaissance aircraft that flew daily missions over the Atlantic and into northern Europe. More accurate forecasts allowed mission planners to time MITO operations for optimal conditions, launching during brief clear periods, planning assembly to occur above cloud layers, scheduling returns to coincide with improved visibility. Specific missions demonstrated both the power and the peril of MITO operations. The first Schweinfurt Regensburg mission on August 17, 1943, demonstrated the potential. The 8th Air Force launched 376 bombers in 2 waves using refined MITO procedures. The first wave departed at dawn, struck Regensburg, and continued south to bases in North Africa. The second wave launched 2 hours later, hit Schweinfurt, and returned to England. The split timing, enabled by MITO efficiency, confused German defences and prevented concentration of interceptors against either target. Though losses were heavy 60 bombers, the missions proved that deep penetration raids were possible with proper coordination. The Big Week operations in February 1944 showcased MITO at its operational peak. Over 6 consecutive days, the 8th Air Force launched missions involving 500 to 800 bombers each day. Using MITO procedures, the entire force could be airborne, formed, and heading toward Germany within 3 hours of first takeoff. This compressed timing meant that weather windows as short as 4 to 5 hours could support full-scale missions. The sustained operational tempo, 6 consecutive days of maximum effort, was possible only because MITO procedures allowed rapid turnaround between missions. D-Day, June 6, 1944, represented the ultimate test. The 8th Air Force launched over 2,000 bomber sorties supporting the Normandy invasion. MITO procedures enabled this massive force to depart from bases across England, form up in the darkness of early morning, and arrive over the invasion beaches in precisely timed waves. The coordination was so exact that formations passed over specific beaches at designated times, hitting predetermined targets in sequence, all while thousands of other aircraft fighters, transports, reconnaissance planes operated in the same airspace. Not a single mid-air collision occurred during departure and assembly, a testament to the refined procedures and trained crews. The raid on Berlin, March 6, 1944, demonstrated MITO's contribution to strategic reach. 730 bombers launched using MITO procedures, formed up, and struck the German capital with P-51 Mustang escort. The compressed launch time meant the entire force arrived over Berlin within a 45-minute window, overwhelming German defences. Previous raids against such distant targets had been impossible not because of enemy resistance, but because standard assembly procedures would have consumed too much fuel and time. By war's end, minimum interval takeoff procedures had enabled the 8th Air Force to launch over 340,000 bomber sorties against Germany. The operational efficiency gains from MITO made possible the systematic destruction of German oil production, transportation networks, and war industries that brought the Nazi regime to its knees. But MITO's influence extended far beyond World War II. The procedures developed for compressing bomber launches became the foundation for all large-scale military air operations. During the Berlin airlift of 1948–49, MITO-derived procedures allowed Allied aircraft to land in Berlin every 90 seconds, delivering 8,893 tons of supplies daily. The entire airlift was essentially MITO in reverse coordinated precision, flying on compressed timelines with zero margin for error. Strategic Air Command in the 1,950 seconds and 60 seconds refined MITO procedures for nuclear bomber operations, developing capabilities to launch entire wings of B-52 seconds within minutes of alert essential for surviving a Soviet first strike. The Christmas tree launch pattern, where bombers would take off at 15-second intervals, was directly descended from the MITO procedures of World War II. Modern air operations still employ MITO principles. Coalition air operations during Desert Storm in 1991 used MITO-derived procedures to launch over 2,000 sorties per day from bases across the Middle East. The guerrilla package strike missions against Baghdad involved dozens of aircraft taking off from multiple bases and converging on targets with precise timing. Exactly the coordination perfected over England 50 years earlier. Commercial aviation owes a significant debt to MITO. Modern airport operations, where aircraft land and take off at 90-second intervals during peak periods, apply the same principles of precise timing, standardized procedures, and compressed intervals that bomber crews pioneered. The air traffic control procedures that safely coordinate thousands of daily flights evolved directly from military operations developed during World War II. The human cost of MITO operations cannot be obscured by operational statistics. 248 bombers lost to accidents during takeoff and assembly, 2,480 men killed before even reaching enemy territory, thousands more injured in emergency landings, non-fatal collisions, and accidents that damaged aircraft but spared crews. These losses represented the hidden casualties of strategic bombing men who died not in combat with the enemy, but in the process of organizing and executing the missions. Their deaths were no less significant, their sacrifice no less meaningful, but their stories are often overlooked in favor of the more dramatic narratives of combat over Germany. The survivors carried their experiences forward into peacetime. Many former bomber pilots became commercial airline pilots, bringing with them the precision and discipline developed through MITO operations. Former navigators became air traffic controllers. Former engineers became aviation safety inspectors. The lessons learned through hard experience over England's grey skies shaped civilian aviation for generations. Minimum interval takeoff procedures represented one of the most significant tactical innovations of World War II, an innovation born not from new technology, but from operational necessity and human determination. In the space of a few years, the 8th Air Force transformed from launching dozens of bombers with 2-hour assembly times to launching thousands of bombers with 3-hour turnarounds. This compression enabled the strategic bombing campaign, supported the invasion of Europe, and contributed materially to Allied victory. But MITO was more than just a procedure. It was a testament to human adaptability under pressure, the willingness to accept calculated risks in pursuit of strategic objectives, and the capability of ordinary men to execute extraordinary operations with precision and courage. The bomber pilots who launched into darkness at 30-second intervals, flying through clouds filled with other aircraft, forming up in compressed airspace with hundreds of other bombers, all while preparing for combat missions that might last 8 or 9 hours. These men operated at the absolute edge of human and mechanical capability. They didn't do it for glory. Most MITO operations passed without public notice, unmarked except in official records and fading memories. They did it because the mission required it, because their comrades depended on it, and because victory demanded it. Today, when we watch aircraft taking off at precise intervals from modern airports, when we read about rapid deployment of military forces, when we see aerial images of 1,000 aircraft formations, we're witnessing the legacy of those bomber crews who pioneered the procedures that made such operations possible. They launched 1,000 planes in hours. They did it repeatedly, under combat conditions, facing both enemy action and the inherent dangers of compressed operations. And in doing so, they wrote a chapter of aviation history that continues to influence how we organize, coordinate, and execute large-scale air operations 3/4 of a century later. The grey skies over England in 1943 and 1944 witnessed a revolution in aviation, not flashy, not widely celebrated, but fundamentally transformative. Minimum interval takeoff procedures changed how wars were fought, how air power was projected, and how humanity understood the possibilities of coordinated aerial operations. And it all started with a simple question. How do you launch 1,000 bombers when there isn't time to do it the safe way? The answer was MITO. Dangerous, demanding, and absolutely essential. The procedure that turned England's airfields into launching platforms for the largest aerial armadas in history. Up next, we have 2 more incredible stories that are waiting for you. Just click the image you want to watch and it will take you there. If you enjoyed this video, make sure to subscribe. It would mean a lot.